I'm going to show you how to determine whether reverse electron flow is needed to make reductant to drive autotrophic processes if you're given the redox couples for a certain type of chemolithotroph. So let's just take an example here, and the example I'm going to use is going to be from the iron bacteria. So the iron bacteria, we're going to have Fe2 plus protons plus half molecular oxygen. So this is an arrow, and that Fe2 plus is going to be converted to Fe3 plus, and the oxygen is going to be converted into water. So the oxygen gets reduced using the electrons from iron. So there are redox couples, and that describes the chemistry that the chemolithotroph is doing. Now let's put that in the context of standard reduction potentials. So again, I'll draw out the redox tower, and as I did before, we'll put 0 here, I'll put negative 0.6 up at the top and positive 0.9 down here at the bottom, and then these are just 0.2 increments until we get down there, which is 0.8. And don't forget the scale here of standard reduction potential is volts. So let's put these couples from the chemolithotroph's chemistry onto the scale. So let's put Fe3 plus Fe2 plus, that couple there, and that has a standard reduction potential of plus 0.76 volts. Now let's put the other part of the equation on there. Let's put the oxygen on there, and then the reduced oxygen, the water, and that has a standard reduction potential of 0.82 volts. So there are those two, and because the standard reduction potential of the Fe3 plus Fe2 plus couple is less positive than the half oxygen water couple, electrons are going to move spontaneously to the oxygen to produce water. So that's going to be spontaneous electron movement, and so the delta G there will be some negative value, and that will be enough delta G to produce a proton motive force and to make ATP. So the organism is following the laws of thermodynamics. But what about if this is an autotrophic species? So that's a species that's going to need to make reductant so that it can fix carbon dioxide. So the reductant that we're going to make here is going to be NADH by reducing NAD+. And there, the standard reduction potential is negative 0.32 volts for this couple. So now the electrons have actually got to go back up the tower. They've got to go from a more positive standard reduction potential to a less positive standard reduction potential. It's obviously negative, so that's less positive. And so we're pushing electrons back uphill there, and so delta G for this reaction is going to be positive. So that reaction is going to be endergonic. That's not going to happen spontaneously. That means that the bacteria is going to have to do some work to drive that chemistry, and so that work can be driven by the proton motive force that's generated from the chemistry that we described down here. So if you find couples in a chemolithotroph which require that you move electrons uphill to the reductant, that is from a more positive to a more negative standard reduction potential in terms of creating reductant, then you're going to be looking at reverse electron flow. And that reverse electron flow requires some work, and that work comes from the proton motive force that's generated as part of the respiratory process.